Hello class, welcome to our Combinatorics lecture for Wednesday, April 8th. By the time you watch this video, our test number 2 will already be posted, right? So I expect you will have already looked at that and perhaps started working on that, and maybe already finished it. So remember, you're going to email that back to me, your solutions to that back to me by Friday, April the 10th at 8:30 a.m., right? So either get those to me on Thursday night or bright and early on Friday morning. We're going to return today to the topic of inclusion, exclusion. So we've been talking about this really throughout the course, right, from the very beginning of the course, and then we looked at it in a more concentrated way last week. But we took out time from Monday's lecture, right, to go over the sample test, right, to give you a review for the test. So today we're going to return to inclusion, exclusion, and look at the more advanced versions of inclusion, exclusion, and look at several examples. We probably will still have a little bit more to do with inclusion, exclusion next Monday, okay, before we finish this topic. All right, so I'm picking up just in the notes where I stopped last Wednesday, and so we were on to version 3 of inclusion and exclusion. Version 3 is just the right number for this theorem, because in this theorem we're going to talk about how to find the cardinality of the union of three sets, right? Okay, so we've already looked at inclusion, exclusion applied to two sets, and looked at some examples, but now we're going to apply inclusion, exclusion to three sets, and then we're going to go on after this theorem to look at the most general version of inclusion, exclusion that applies to any number of sets, 2 or 3 or 4 or as many, an arbitrary number of sets, okay? But to understand that more general version of inclusion, exclusion, you do have to, it helps to have seen inclusion, exclusion applied to just a couple of sets, or in this case, to 3 sets, right? All right, so here's the statement of the theorem. It looks like the statement of inclusion, exclusion theorems, the earlier versions of inclusion, exclusion theorems, right? Except now we're going to be considering 3 sets instead of just 2 sets. So suppose we have 3 sets here. I'm just going to label them A, B, and C. And remember, they're not necessarily disjoint. If the sets are disjoint, then it's really easy to count the union of A, B, and C, right? So the complications arise when the sets A, B, and C overlap, right? When their intersections are not empty, okay? And so what inclusion, exclusion says about the cardinality of the union of these 3 sets is as follows, okay? To find this cardinality, just take the sums of the sum of the cardinalities of the 3 individual sets, right? Okay, so you're going to add up the size of the 3 individual sets. But when you do that, as we'll see when we demonstrate why this theorem is correct, when you do that, you're going to be overcounting elements in the union. All right, so what we have to do to compensate for that is, according to inclusion exclusion, we're going to subtract off the sizes of the intersection, the pairwise intersections of the 3 sets. So you look at every pair of the 3 sets. Notice there's going to be 3 of them, okay? So you look at every pair of the 3 sets, take their intersection, and then you subtract off the size of those pairwise intersections. Well, it turns out, and again, we'll demonstrate this in just a moment, when you subtract off those pairwise intersections to compensate for overcounting, when you add up just the cardinalities of the 3 sets, it turns out you subtract a little bit more than you need to in this case, all right? So what we have to do is compensate for that and add back in, as it turns out, the cardinality of the intersection of all 3 sets, okay? So look at where all 3 sets overlap simultaneously. Look at the size of this intersection, and you want to add the size of that intersection back, Okay, so you already get a feel right for how the this terminology inclusion exclusion arose, right? We're going to include, right, the cardinalities of the three sets, right? When we're counting the cardinality of the union, we're going to include the cardinalities of the individual sets, and then we subtract off, right? We exclude the cardinalities of the pairwise intersections of the three sets, okay, and then we include again, okay, the cardinality of the intersection of all three sets, right, okay, together. So so you got this process of adding and subtracting and then adding again, right? That's how the terminology inclusion exclusion comes about, and this same pattern is going to reveal itself again when we look at the more general version of inclusion-exclusion, where we're computing the cardinality of the union of an arbitrary number of sets, not restricting it to just three. All right. Okay, but before we get to that more general version, we need to look at some examples of Theorem 5 in practice. But before we do that, I want to give you it's not really a completely formal proof of Theorem 5, but it's a pretty rigorous proof. I think it's a pretty good argument as to why this Theorem 5, this version 3 of inclusion-exclusion is correct. And just like with when we were proving version 2 of inclusion-exclusion that applied to just two sets, a Venn diagram is really helpful here. All right, so let's make a Venn diagram of the union of three sets. So I've, in the typical Venn diagram fashion, right, I've represented these sets as these big circles, and since these sets are not disjoint, right, they may overlap, right, in particular ways. Okay, so here you see the intersection of A and C. This is the intersection of B and C. Here's the intersection of A and B, right? And then right here in the middle, right, is the intersection of all three of the sets. Okay, now what I've done is I have identified some elements that are in particular locations in this union of the three sets. Okay, so this element A, for instance, is in the set A, but it's not in any of the other two sets. Okay, so it's not in any of the intersections of A with the other two sets. This element B is in the set B, but it's not in any of the intersections of B with the other two sets. The same, likewise for this element C, right? It's in the set C, but not in C's intersection with either of the two sets. And this element Y would be in the intersection of A and C, but not in B. Okay, so it's this element Y is in both A and C, but it's not in B. This element X is in both A and B, but it's not in C. This element Z is in both B and C, but it's not in A. Okay, and then finally this special element W here, right? This element is contained in all three of the sets. All right, so so here I've just repeated that inclusion-exclusion formula, which tells us how to find the cardinality, right, of the union of these three sets, right? And so what I'm going to do is show you how these individual elements are counted in this formula, so you can get an idea of why we have to do these subtractions and why we have to do this addition in order to properly count the cardinality of the union of the three sets. All right, so let's look at how the formula is going to work, right? Okay, so again, to find the cardinality of the union, it says find the add up the cardinalities of all three of the sets. Okay, all right. So when you add in the the cardinality for A, right? Okay, notice you're going to be counting once, right? All the elements in A. So that means A gets counted one time, right? When we add in this number, Y gets counted one time, right? Because it's in A. W is in A, so it gets counted one time. And notice X is also in A, so it gets counted as well. I'm going to have a hard time squeezing in where I'm going to put that 1. but let's put it right here, right? So when we add in the cardinality of A gets counted once, Y gets counted once, W gets counted once, and X gets counted once, right? Because all of those elements are in A. Same thing for B, right? So when we add in the cardinality of B, all the elements in B are going to get counted, right, when we add this number. So that means B now is going to be counted once. Z is going to get counted now. But notice W is going to get counted again because it is in B as well as A, right? So notice at this point you have counted W twice, right? Okay, and also X is going to get now counted twice, right? Okay, because it is in both A and B. Now when you add in C, what happens? Well, this element now gets counted, right? Okay, because it's in C. But notice Z gets counted again, right? Because it's in C. Y gets counted again, right, because it's in C, and W, lucky W, also being in C, is now going to get counted. So notice what you've done here is you've overcounted, right? In the union, you want to count all of these elements once, but X has been counted twice, right? Z has been counted twice, W has been counted 3 times, and Y here has been counted twice, right? So we have overcounted some. So here's how we're going to compensate for that, right? So I'm going to start subtracting out the overcounts for these elements. So the formula says first subtract A intersect B. So all the elements in A intersect B we're going to subtract out, right? Well, what is in A intersect B, right? Well, that's X and W, right? So from the counts for X and W, I am going to subtract 1, right? Because I'm subtracting out this the cardinality of this intersection. So X was overcounted, but now I'm going to subtract 1 out, right, because it's in A intersect B. W is now going to get subtracted once out, right, because it's also in the intersection of A and B. And then that's it, right? Okay. So we've only counted now X once, right? And but W, notice now, has been counted 3 times, right? Okay, or still twice, right? Now, we're going to subtract out A intersects C. So what things are in A intersects C? Well, we want to subtract out Y once, right? Because it's in A intersects C. And now W also is in A intersects C, so it's going to get subtracted out, right? Okay. And now we want to subtract out B intersects C. So what things are in B intersect C? Well, Z is in there, right? So we're going to subtract off one of its counts, right? And then, but W is also in B intersects C. So notice what's happened here now is when you subtract off these intersections, look, everything is counted properly, right? A is counted once, X is counted once, B is counted once, Z is counted once, C is counted once, Y is counted once. But W, unfortunately, is not counted at all, right? So you see we've undercounted because W now is missing from our count. So how do we fix that? We have to add that back in, right? So we have to count the intersection of all 3 sets. The only thing that's in the intersection of all 3 sets in this picture is W. So I'm going to come back here and add back in W, right? And look, at the end of this process, we have counted all these elements right exactly 1 time. So we have exactly the correct count for the union. Cool. See how that works, right? Okay. So that's not a completely formal proof, but that's a pretty good demonstration. I think we could turn that into a formal proof if we worked on that. That's a pretty good demonstration, right, of why this Theorem 5, right, is correct. Here's just what I sort of said verbally written down in words. Okay. All right, so there's our demonstration of why Theorem 5, the third version of inclusion exclusion, is true, right? Now, I'm going to present also, like we did for the second version of inclusion exclusion, I want to present the complement version of Theorem 5, okay? Because we often apply Theorem 5 in the context of computing the complement of a set, okay? And so so this is just this Theorem 6 is just an immediate consequence of Theorem 5, right? So it says if you have 3 subsets, right, of a universal set, and suppose you want to find the size of the complement of the union. So take the union of the 3 sets, and then you want to find the cardinality of the complement of that union. All right. Well, from elementary set theory, right, we know that the complement of a union is the same as the intersection of the individual complements, right? So A union B union C complement is the same as A complement intersect B complement intersect C complement. So that's just that line, that first line of this equation is just, that's just elementary set theory. But we also know, right, that to find the complement, the size of a complement of a set, right, we subtract the set, right, the size of the set from the size of the universal set. Remember, the universal set is the set in which all these A, B, and C are all subsets of the universal set. Okay, so we know this complement is the universal set minus the size of this union. But now we can calculate, right, the size of this union using inclusion exclusion. So now we can apply Theorem 5, right, to compute. So we can use Theorem 5, right, to find out what the cardinality of this union is. And so when you do that, notice you're subtracting here, right? So when you apply Theorem 5 to find the cardinality of the union, right, you end up with showing that the cardinality of the complement is the size of the universal set minus the sizes of the cardinalities of the individual sets plus the cardinalities of the pairwise intersections of the sets, and then minus the cardinality of the intersection of all 3 sets, right? This minus sign sort of reverses, this minus sign sort of reverses all the signs in Theorem 5, and you end up with this formula, okay? So again, if you want to find the size of the complement of the union of 3 sets, remember that's the intersections of the individual complements, this is right here, right, is the formula that that you can use, okay? All right, so it's, again, just a directly comes from Theorem 5. And again, the reason that I'm stating Theorem 6 is, again, we often use inclusion, exclusion in the context of computing the size of the complement of a set. All right, well, let's look at some examples then. Now, when you're applying inclusion, exclusion version 3 or the more general version that we're going to learn about in a minute here today, these problems are going to be rather lengthy and involve lots of computations, even if they're conceptually easy to understand how the solution is going to come about, right? There's going to be some computations involved, and so so I didn't want to write down all of the computations here while I was speaking. I went ahead and started filling in some of the solutions to these problems, just to keep ourselves within the appropriate time limit today. All right. Okay, so that's why some things are already written here. All right, so let's read the problem and see if we can understand it. So this problem 3 says, find the number of integers between 1 and 1200 inclusive. So that could include 1, but also include 1200. That are divisible by either 5 or 6 or 8. Okay, so I want to know how many integers between 1 and 1200 are divisible by 5 or 6 or 8, right? Okay, so let's see if we can count that set. And this is a perfect example of applying the third version of inclusion exclusion. Let me show you how. Okay, all right, so here's what I'm going to do. I'm going to let A be the set of integers that's divisible by just 5, right? We're trying to count the set divisible by 5 or 6 or 8, but I'm going to let A be just the set divisible by 5. All right. So what numbers between 1 and 1200 are divisible by 5? Well, there's quite a few, of course. In fact, every fifth integer, right, will be divisible between 1 and 1200 will be divisible by 5. So 5, 10, 15, 20, right, 25, etc., right, including all the way up to 1200 also is divisible by 5, right? So it's easy to compute the cardinality of A, right? Because every fifth integer between 1 and 1200 is divisible by 5. So if you just take 1200 and divide that by 5, that's going to give you, right, the size of this set A, right? And that's going to be, that's of course an easy quotient to compute. That's going to be just 240. All right. Now I'm going to make corresponding definitions of sets 4, 6, and 8. So I'm going to let B be the integers divisible by 6. All right. So integers between 1 and 1200 divisible by 6. And so we can easily compute this set B. That's going to be 1200 divided by 6, right? Because every sixth integer between 1 and 1200 is divisible by 6. That includes 1200, right? Which is divisible by 6. So you get 1200 over 6, which is 200. So there are 200 integers, right? Between 1 and 1200 divisible by 6. And now again, I'm going to make this a corresponding definition for 8. So I'm going to let C be the integers between 1 and 1200 divisible by 8. Okay, and by the same logic as we used for A and B, right, we can see that the cardinality of C is going to be 1200 divided by 8, which I think is 150. Yeah, I'm pretty sure that's right. Okay, so so we notice the cardinalities of A and B and C, right? But we cannot just add those cardinalities together, right? We cannot just add those cardinalities to find the cardinality of the union of these three sets, right? And by the way, it's the union of the three sets that is the answer to the question, right? Okay. We want integers divisible by 5 or 6 or 8, correct? So that would be numbers in set A or in set B or in set C, correct? Divisible by 5 or 6 or 8. Well, okay, by the way these three sets are defined, right, then the answer to this question is just going to be the cardinality of the union of these three sets. But if we just add the individual cardinalities together, right, those are easy to compute, as we showed here, right, we will overcount, correct, because some integers are going to be in the intersections of these three sets, right? Some integers are divisible by both 5 and 6, right? Some integers are divisible by both 6 and 8, right? Some integers are divisible by both 5 and 8, right? Okay, so and some integers are divisible by 5 and 6 and 8, right? So we will have overcounted, right, if we just add the cardinalities of the three sets. So we just compensate, right, according to inclusion exclusion. So inclusion exclusion says, well, to compute the cardinality of this union, right, well, indeed, you do add the cardinalities of the three individual sets, right, but now we have to subtract off the cardinalities first of the pairwise intersections, correct? So I look at every possible pair of sets here and calculate the cardinality of the intersection of that pair, right? So there are three possible pairs of sets here, A and B, and A and C, and B and C. And so I compute the cardinalities of the intersections of those pairs. All right, let's see if we can figure out what those are. Oh, but before I do that, there's one other line here, right, in my formula, correct? Because now, when I just subtract off those intersections, right, I have gone too far. So now I have to add back in, right, the cardinality of the intersection of the three sets. All right. Now, of course, if we cannot find the cardinalities of these intersections, then, although this is a nice equation to write down, it wouldn't be of much practical use to us, right? Okay, but I think in this example, right, we can compute the cardinalities of the intersections, right? By the way, of course, we already computed the cardinalities of A, B, and C. Let me throw those in here. So that is 240 plus 200 plus 150, right? Now, what do we want to subtract off? The cardinality of A intersect B. Well, look, if a number is in both A and B, right? If a number is in both A and B, that means it is divisible by both 5 and 6. But a number that's divisible by both 5 and 6 will be divisible by the product of these two numbers, which is 30. So the intersection of A and B is just going to be all the numbers from 1 to 1200 that are divisible by 30. Okay, and well, that's pretty easy to calculate, right? That's going to be 1200 divided by 30, right? Okay, so that we have to subtract off. What about A intersect C, right? Okay, that's going to be numbers divisible by both 5 and 8. But if a number is divisible by both 5 and 8, that means it's divisible by the product of 5 and 8, which is 40. So and that's easy to compute, right? The number integers between 1 and 1200 divisible by 40. There would be 1200 over 40 of those, right? And then finally, well, let's see, B and C, we want numbers divisible by both 6 and 8. That would be numbers divisible by the product of those two. So that would be this many numbers, right? Take 1200 and divide by 48, okay? And now, what do we add back in, correct? What do we add back in here? Well, we want to add back in the intersection of the three sets, and that would be numbers divisible by 5 and 6 and 8, and I think that's numbers divisible by the product of these, right? Which would be 240, and there would be 1200 over 240 of these. Let's see, what does this reduce to now? So 240 plus 200 plus 150, that's what? 440 plus 150 is 590 minus, let's see, 1200 over 30 is 40. 1200 over 40 is 30, right? Okay, and then 1200 divided by 48. How much is 1200 divided by 48, right? Okay, is that 25 or something? Yeah, 25. All right, exactly. So we subtract off 25, right? And then we want to add back in, right, 1200 divided by 240, and that's easy to see that that is going to be 5. So there's our total, right? Okay, 590 minus 70. Is that exactly 500? Is that what that comes out to be? Okay, looks that way, right? 590 minus 70 is 520, minus 25 is 495, plus 5 is 500. Nice. Okay, so there are exactly 500 numbers, right, between 1 and 1200 that are divisible by 5 or 6 or 8. That's pretty straightforward problem, right? Okay, let's now look at an example where we're going to apply Theorem 6. So we're going to solve this problem using complements. Okay, so let's see what it says. How many permutations of these letters So I want you to notice there are 9 letters there, and we are fortunate that all of those letters are different. Okay, right? So we've got 9 distinct letters, and so we want to know how. We want to know how many of the permutations of those 9 distinct letters are such that none of the words math, is, and fun, right? Math is fun. None of those words would occur in the permutation. Okay, so none of the words math, is, and fun occur as consecutive letters in the permutation. Okay. So, by the way, notice you can spell all of those words, math and is and fun, right? You can spell all of those from the letters in this list, right? Okay, but we want to find permutations where none of those words is embedded in the permutation. All right. All right. So here's how we're going to think of this problem as a problem of complements. All right, so watch this example, because this logic is going to get repeated in some of our later examples. All right, so first I'm going to choose as my universal set. Since I'm solving this with complements, I'm going to have a universal set. So I'm going to let B be the I'm going to let U here. I'm sorry, be the set of all permutations of these letters, right? Okay, so all permutations of these 9 letters, and it's very easy to compute what the cardinality of U is, right? Because since all of these letters are distinct, right? We don't have any repeated letters. Then all we're really doing here when we're computing the cardinality of U is asking how many permutations there are of 9 distinct objects, and that we know from for a long time, right, is 9 factorial. So we know the size of U here, right, is 9 factorial. Let me write that here. And actually, I think I know. Let me see if I've got this written down somewhere. Oh yeah, I know how big 9 factorial is. So you can compute this with your calculator, but it turns out that 9 factorial is 362,880. Okay, so that's going to be my universal set for my complement. All right, and now let me show you how we're going to apply now inclusion, exclusion. All right, so I'm going to let A here be permutations of these, again, these 9 letters that contain the word math. All right, so where you have M-A-T and H in that order all together in the permutation. Okay, so that's going to be my set A, and then my set B is going to be permutations that contain the word is. All right, permutations that contain the word is, and then C is going to be permutations again of these 9 letters that contain the word fun, F-U-N, those 3 letters in sequence in the permutation, right? Okay. Now, I want to point out before now I'm going to actually compute the cardinality of A, B, and C here in just a second, because we'll need that. And these cardinalities are easy to compute. All right, we're very skilled at computing, sizes of permutation sets, right? Okay, but I want to point out here that the reason I define these 3 sets, okay, is because if you take the intersection, not the union, but if you take the intersection of the complements of these 3 individual sets, notice that that is the set that we are asked originally to count, right? Okay, and just read this off of the page, And you can immediately see why this intersection of these complements is the set that we're really looking for here. Because think about what this intersection is telling us, or what this intersection contains. It contains permutations that don't have the word math in them, right? And don't have the word is in them, and don't have the word fun in them, right? Okay. See, A complement is words not containing math. B complement is permutations, words not containing is, and C complement is permutations not containing fun, right? Okay, so if you combine all of those, right? No, not math, not is, not fun. That's exactly the set that we were asked to count. Okay, so if I can determine the cardinality of this set, then I will have answered the problem. But we know how to compute the cardinality of this intersection, right? That is exactly Theorem 6, okay? Because Theorem 6 tells us, right, that to compute the cardinality of the intersection of the complement, you're going to take your universal set cardinality, right? Subtract the cardinalities of the three sets A, B, and C, right? Then add back in the cardinalities of the pairwise intersections of A, B, and C, and then subtract off the cardinality of the intersection of all three sets, right? Okay. So if I can compute all of these cardinalities, just insert them into this formula, you know, do the addition or the subtraction, and do the arithmetic, in other words, then I will know how many permutations there are that don't contain the words math or is or fun, right? Okay. All right, so see, I've set this up now as an inclusion-exclusion problem with complements, right? And of course, this is what I've written here is really just a restatement of Theorem 6. All right, now let's see if we can use our counting skills now to compute all these several cardinalities right here that we need to compute. Well, right, we've already calculated that, right? That was 9 factorial, right? So that was 362,880. All right. Now let's see if we can figure out how big is A, how big is B, and how big is C. If we can figure out A, then we'll probably have a pretty good clue as to how big B and C are as well, right? So let's think about finding A. All right. Here's how you can think about A, right? Okay, the set A. Remember, A is, we're computing A, right? Not A complement, right? We're just computing A. A, the size of A. A is permutations that contain the word math, all right? So if you want permutations that contain the word math, just think of the word math as one block, right? Okay, because those letters all have to occur together, right? And then the other letters, right, can occur in any other order, but these letters have to occur in this exact sequence, right? All right. So what are the other letters? Well, let's see. There would be F and I, right, and N and S and U, correct? So when you're computing the size of A, what you're really doing is looking at arrangements of 6 things, right? Okay, this whole block of letters math, and then these other 5 individual letters, correct? Okay. So permutations that contain the word math are really just permutations of these 6 items, right? This block of 4 letters, right? And then these other 5 individual letters. In other words, we're just looking for permutations of 6 items, right? Okay? And we know how many permutations there are of 6 items, though. That's going to be 6 factorial. What about B? Now we have a very important clue for B, right? How big is B going to be? Well, when you're figuring out permutations that contain the word is, what you would be doing is thinking of these two letters, I'm sorry, this word as a single block, correct? So those letters must occur together, right? So think of those as a single item. And then the other 7 letters, right, that you have available, they could be mixed up in any order, correct? So what you're really doing is you're permuting 8 objects, right? These two letters together, and then the other 7 letters, right, that you have to fill in, right, to get a permutation. Well, how many ways can you arrange 8 objects? It's 8 factorial, correct? What about for fun? Okay, well, for fun, let's see, think of the letters in fun, right, as a single unit, right? And then we have to combine those with sort of any arrangement of the other 6 letters, correct? Okay, so you've got 6 letters plus this block of letters, and they to permute. So that's 7 items that you're going to permute, and there are 7 factorial ways of permuting 7 items. So neat, right? We know what these cardinalities are, correct, right? This is going to be 6 factorial. B here is going to be 8 factorial, and C is going to be 7 factorial. So we're well on our way here, right, to filling in this formula. Remember, U was 9 factorial. I already wrote that down as 362,880. All right, now let's look at the intersections, though, right, because we've still got 4 other cardinalities that we have to compute. Let's look at the last one first, because that one is very easy to calculate, right? A and B and C means that you would have a permutation that contains this word, math, this word is, and this word, fun. But you don't have to have these 3 words in this order, right? Okay, you don't have to have math is fun. You could have is fun math, right? Or fun is math, right? Or math fun is, right? But you will have, again, these blocks of letters all together, right? Okay, because in this intersection, you have to have a permutation that contains the word math and contains the word is and contains the word fun. Well, so essentially what we're asking for is how many ways can we permute these 3 words, right? Well, how many ways can you permute 3 objects? That's pretty easy, right? That is 3 factorial. So we know this intersection is 3 factorial, correct? That gives us a strong clue now for computing the pairwise, the cardinalities of the pairwise intersections as well. So what about A intersect B? That would be a word, right? A permutation that contains these 2 words, math and is, right? Okay, you don't have to have math before is, or right? Okay, and you've got other letters that you have to fill into the permutation, but these 2 words must appear in the permutation. All right, so that means you can think of math, right, as a block of letters that has to occur together in your permutation, is as a block of letters that has to occur together in your permutation, and then you've got 3 other letters that you have to fill into the permutation. So altogether, you're permuting 5 objects, right? The word math, the word is, and then the 3 other letters that you have to fill into the permutation, right? So the size of A intersect B, right, is going to be, that's easy, right? That's going to be 5 factorial, right? 1, 2, plus the 3 other letters. That's 5 things, right? 5 factorial. What about A intersect C? Well, that means you've got a permutation that has the word math and the word fun, right? So you're going to think of math and fun, right, as being 2 blocks, right? And then you would have to fill in your that are going to appear in your permutation, 2 items that are going to appear in your permutation, right? And then you would have two other letters that have to be inserted in the permutation. So in effect, you're permuting 4 objects, right? This word, and the 2 other letters. And of course, there are 4 factorial permutations of 4 objects. And then finally, what about the last one here, B intersects C? Well, using just exactly the same logic, right? Okay, this turns out to be, I think, what does that turn out to? Did I do that right? Oh no, B intersects C, right? Okay, so this turns out to be 5 factorial again? No, is that right? That's 1, 2, and then, oh, that's 6 factorial, correct? All right, so yeah, that one is 6 factorial. Okay, now you're done, right? All you have to do is fill in these values. Let's see if I know what these are. Okay, so 9 factorial is, I mentioned, 362,880. 7 factorial is 720 minus 8 factorial. That turns out to be 40,320. That's 40,320 minus 7 factorial is 5,040. Then plus, now we're adding in 5 factorial, which is 120, plus 4 factorial, which is 24, plus 6 factorial, which is 720 again, and then minus the 3 factorial, which is 6. And when you add up all those numbers, that turns out to be quite a large number there, 317,658. By the way, I didn't mention this example is from the book, okay, and this is on pages 166 and 167 from the text. So if you want to read the book's explanation of this problem, you can, okay, on these pages. So there it is. There's our answer. Nice, right? Okay. I'm going to pause here for just a second, and then we're going to state here the final general version. So this is version 4 of the inclusion-exclusion theorem. So we're going to use this version of inclusion-exclusion to find the cardinality of the union of an arbitrary number of sets. All right, and then we also have this Theorem 8 restated in terms of complements. That is Theorem 9. So I'll pause here for a moment, and then we'll come back and look at the statement of these theorems, and then we want to look at an example making use of these theorems. Okay. All right. So I'll be back in just a second here. All right, so we're back, and so here, as I mentioned, is the most general version of inclusion-exclusion. All right, so I'm calling this version 4, and this formula that's given in this theorem can be used to compute the cardinality of the union of an arbitrary number of sets. So suppose you're given a group of sets. I'm just supposing there are m of them. Okay, so a sub 1, a sub 2, a sub 3, up to a sub m. But this subscript m, right, can be any positive integer, right? And suppose we want to find the size of the union of those m sets, right? But keep in mind that we're not assuming in inclusion-exclusion, right, that the sets are disjoint. So when you look at the statement of this inclusion-exclusion formula for computing the cardinality of the union. It looks very daunting, but there's a very clear pattern to it. So it's really easy to use. Well, I'm not gonna say it's easy to use, but it's easy to understand how the formula works. All right, so because it echoes very much Inclusion Exclusion version 2 and Inclusion Exclusion version 3. All right, here's what the formula says. Here's the notational version of the formula, but let me explain to you in practical terms how the formula is actually working. Right, so what the formula says is you want to take first, right, add up the cardinalities of the individual sets, right? So you just add up all of those cardinalities, right? So you add up the cardinality of A1 plus the cardinality of A2 plus the cardinality of A3, etc., up to the cardinality of A sub m. Okay, remember this sigma, it indicates a sum, all right? And so I'm adding up the cardinalities of the individual sets. Now, that overcounts though, right? So just like it did in version 2 of Inclusion Exclusion and version 3 of Inclusion Exclusion, right? This will overcount. So we have to compensate for the overcounting. So first, we subtract off now the cardinalities of the pairwise intersections, right? So you look at every pair of your M sets, find the intersection of every one of those pairs, and you subtract those off. Okay, so subtract off the pairs. All right. It turns out that when you do that subtraction, you have undercounted. So we have to add something back in to compensate for the undercounting. Here's what we add back in, right? So we add in, take the intersection of 3 sets at a time, but you have to look at all possible intersections of 3 sets. All right, so take the intersections of 3 of the sets at a time, add those cardinalities back in. All right, well, when you add these cardinalities back in, it turns out now you have overcounted a little bit, so you have to compensate again by subtracting off. What do you subtract off? Now you take the intersection of 4 sets at a time, but you must look at all possible sets of 4 of the sets, right, and compute the intersection and subtract that off. And then you just continue that inclusion-exclusion pattern, right? So cardinalities of the individual sets, right? Subtract off the cardinalities of the pairwise intersections. Add back in the cardinalities of intersections of 3 sets at a time. Subtract off the cardinalities of the intersections of 4 sets taken at a time, right? And so on and so forth until you get to, notice you're alternating addition and subtraction, right? Until you get to where you're finally either adding in or subtracting out the intersection of all of the sets, right, taken at one time. Okay. So again, it's going to be this alternating, adding and subtracting, including and excluding, right? Okay, and then you look at intersections of groups of the sets, right, that you're trying to compute the union of. All right, now in Theorem 9, I've got this theorem restated in terms of complements, okay, just like we restated the earlier versions of inclusion exclusion in terms of complements. But I don't want to look at this this complement theorem at the moment, although it's easy to understand. It's very similar to our prior complement theorems. It comes directly from, the Theorem 9 comes directly from Theorem 8. But let's look at an application of Theorem 8. So a very simple application of Theorem 8, just to get you sort of used to how the inclusion-exclusion formula is working. So I'm going to take one of our prior examples, and we're just going to soup it up a little bit. All right. Let's find the number of integers between 1 and 10 inclusive. Okay, between 1 and 10 inclusive, right, that are divisible by 5 or 6 or 8. Or 10, okay? All right, so so very similar to that earlier example, right? Okay, so just like in that earlier example, I'm going to create some sets, but in this case, I'm going to create 4 sets. So I'm going to let A sub 1 be the integers divisible by 5. And remember, we know how to count that, right? Since every fifth integer from 1 to 1200 is divisible by 5, we just can let that, we can just calculate that easily. Just take the size of that set easily, right? Just take 1200 divided by 5 and you get 240. So the number of integers divisible by 5 is 240, right? Let's let a sub 2 be integers divisible by 6, right? So that is going to be, the cardinality of that set is going to be 1200 over 6, which is 200, correct? So this is just like the earlier example. Let's let a sub 3 be the integers divisible by 8. So the cardinality of that set is going to be 1200 divided by 8, which is 150, right? And then now we have another set, though. Let's let a sub 4 be the integers divisible by 10. And this set was going to be of size 120, all right? That's just 1200 divided by 10, since every 10th integer is divisible by 10. So what we're looking for here now is, let me fix this. What we're looking for now is the cardinality of the union, right, of these 4 sets, because we want numbers that are divisible by 5 or 6 or 8 or 10, right? So if we can compute the cardinality of this union, then we will know, right, the number of integers divisible by 5 or 6 or 8 or 10. Okay, all right, so here we're trying to compute the cardinality of the union of 4 sets, right? So let's apply now our inclusion exclusion. All right, so now just remember, now the way that formula works, very easy to understand. First, you add up the cardinalities of the individual sets, right, which we already know from which we've already calculated, right? So I'm going to add up the cardinalities of the individual sets, right? Now we have to subtract out the cardinalities of the pairwise intersections of the sets. Make sure you write down every pairwise intersection, okay? So you have to be careful about this step, right? Make sure you write down every pairwise intersection. So let's see, what are those? A1 intersect A2, A1 intersect A3, A1 intersect A4, right? And then I guess we would also have A2 intersect A3, right? And A2 intersect A4, correct? And then what's left? So A2 with 3, 2 with 4, and then I guess next would be what? 3 with 4? Right, is the last one. That's A4, by the way, okay? So subtract off those pairwise intersections, but make sure you have accounted for make sure, right, you have accounted for every pair. Now add back in, right? So include, exclude, include, right? What are we going to add back in? Now you have to look at the intersections of 3 of them at a time, okay? So you must make sure you get every combination of 3 sets and compute the intersections of that, and compute the cardinality of that intersection. So let's see, I can have A1 intersect A2 intersect A3. I can have A1 intersect A3. I'm sorry, A2 intersect A4, right? Okay, and then what else there? A1 intersect A3 intersect A4. Okay, and then I think there's one more, because we can have A2 intersect A3 intersect A4. 4. That's it, okay? So that's every possible combination of 3 of these sets. All right, now what do we subtract off? You're subtracting now. Now it's every intersection of 4 of the sets, but there's only 4 sets, right? So you only get one intersection here that you have to subtract off, okay? All right, so let's see. Let's see if we can compute now all of these cardinalities, right? Well, since this is really just division, right, I think these are really pretty easy to calculate, right? So we calculated the these 4, right? That's 240 plus 200 plus 150 plus 120, right? Now we subtract off intersection of A1 and A2. So that's numbers divisible by both 5 and 6. So if it's divisible both 5 and 6, right, that means it's divisible by 30, correct? Okay, and so how many are divisible by 30? Looks like there's 40 of those, right? Okay, how many of these integers are divisible by 30? It's going to be 1200 over 30, which is 40 of those. A1 and A3 divisible by both 5 and 8, that means divisible by 40. There's going to be 30 of these integers between 1 and 1200 divisible by 40. Divisible by both 5 and 8, right? Okay, this is A1 A1 intersect A3 I did, right? Okay, no. Did I do this right? So A1 intersect A2, that's 40. A1 intersect A3 is 30. Now we have A1 intersect A4. So we want numbers divisible by both 5 and 10. That would be numbers divisible by 50. And so there are going to be 24 of those, right? Okay. And then A2 and A3, that's numbers divisible by both 6 and 8, that's numbers divisible by 48. We calculated that before. That was 25, right? And then numbers divisible by 2 and 4, right? So this is numbers divisible by both 6 and 10, right? So that's divisible by 60, which is 20 of those, right? Okay. And now numbers divisible by both 8 and 10, that's numbers divisible by 80, okay, and I think there are 15 of those, okay. Numbers between 1 and 1200 divisible by 80, there's 15 of those. Oh, wow, okay, so see, lots of arithmetic to do here, right? Okay, all right, now let's come and now let's add back in what we need to add back in, right, which are the intersections of triples, right, in the 3 sets, okay? So let's see, one intersection of A1, A2, A3. That would be numbers divisible by 5 and 6 and 8, right, okay? So that's numbers divisible by 240, and I think we discovered before that was 5, right? What about A1 intersect A2 intersect A4? That's numbers divisible by 5 and 6 and 10, right? So that's numbers divisible by 300, and there are going to be 4 of those, plus A1, A3, A4, that's numbers divisible by 400, right? If it's numbers divisible by 5 and 6 and 10, 5 and 8 and 10, that means it's divisible by the product of those, which is 400. So that's going to be 3. And then finally, the last ones here, numbers divisible by 6 and 8 and 10, right? That's numbers divisible by 480. So numbers between 1 in 1200 that are divisible by 480. Let's see, how many of those are there going to be? Is it, I'm not sure there, right? There may only be 2. Oh, yeah, okay. There's only 2 here, numbers that are divisible by, between 1 and 1200 divisible by 480. It would be 480 and 960, and that's it, okay? And then finally, what do we finally subtract off here, right? Numbers divisible by all of these values, right? Okay, and I think that is 0. Nice. Okay, so add up all of those numbers, and which I'm not going to do here, but that gives us the answer there to our question. Okay, so there's our first application of inclusion exclusion. So our next 2 applications are going to be a lot more challenging. So I don't have time to get into the next application today because it's going to take more than the 10 minutes that we have left. So we'll look at that on next Monday. So that will be Monday the 13th, right? And so we'll look at our more advanced applications of inclusion exclusion. Okay. All right. So good luck with your test. Okay, that you're working on, and I'm sure you're going to do well on it, though. Remember Monday's lecture, I gave a review of the sample test. So if you have not looked at that, you should look at that before you work on the test, because that's going to help you with working on the test. Monday's lecture, the lecture for Monday, April 6th. All right, guys. So I will see you next Monday, April 13th.